So in this chapter, we're going to be talking mainly about the sources of magnetic fields. All right, we're going to cover the Biot-Savart law. I'll introduce that. And we're going to talk a lot about the forces that parallel current-carrying wires feel. And that has super important applications in transmission lines and basically how you and I get our power every day in our home. And I don't think we're going to be able to cover Ampere's law. I might just briefly introduce the concept of it, but I might have to cut this section out for the sake of time. Okay, but we'll try to get to there. And so basically, in the previous chapter, we talked a lot about the forces that moving charges feel when they're in a magnetic field. Okay, we talked a little bit about the field itself, but we're going to focus basically in this chapter on the field itself. All right, the field that is created by moving charges. And so in this picture here, what the heck is this, right? You may be thinking, what is this? Well, these orange blocks that are kind of arranged in a somewhat circular pattern, these orange blocks are current carrying wire, okay? Lots of loops of wire, ton of loops of wire. And what are they there for? They're there to create a magnetic field, all right? What's the orientation of this magnetic field? Well, let's use our right-hand rule, what we talked about in the previous chapter, to figure that out. So if our current is in a circle like this, okay, let's say the current is moving in a clockwise, sorry, that's not how clocks work, in a counterclockwise direction. Let's use our right-hand rule to figure out the magnetic field direction. So if the right-hand rule that we will use for this is thumb and direction of current. Okay, thumb is in the direction of the current. And then our fingers are going to curl around the current direction. So we're going to be looking basically, if I'm right here, at the back of the hand. Okay, and my fingers are going to be curling down and rotating around the wire. Okay, so coming out of the page, going into the page. Okay, going out of the page on the top. That's not a good. Okay, going out of the page on the bottom, sorry about that, and into the page on the top. Do you see that? Same all the way around. Out of the page on the bottom, into the page on the top. And so what happens is they all add up to a B field in the very center coming out at you. And if you turn the current around the other direction, well, that would just be the B field pointing down the tube this way. And so what we've done is by now curling the current wire, we're creating a straight magnetic field, right? If you go back a few slides, remember we had a straight current carrying wire, and we saw that the magnetic field did loops around it, right? Well, what we did here in this application of the I believe this is in the Large Hadron Collider, is we have curled the current and created a longitudinal magnetic field. Okay, so we're going to be talking about stuff like that. Basically, this is all about the sources of magnetic fields. So, as I mentioned before, right, moving charges generate magnetic fields. Just like a stationary charge generates an electric field, okay? Well, so basically moving charges create both electric and magnetic fields. So let's look at how we determine the direction and magnitude of the magnetic field created by a moving charge, a single charge. So imagine we have a charge. Let's go ahead and put an XYZ axis over here. Let's make this XYZ. Let's do this. Let's make the Y up here and then the Z over here. So let's say we have a charged particle. Let's make it a positive particle. And it's moving, let's just say it's currently at the origin, moving to the right along the X direction, okay? It's a red, it's a positive particle. So, and that's a V. I'll make it a little bit nicer. That didn't make it any nicer. There we go. So the question is, okay, this particle's moving. It's moving in the X direction. All right, what's the magnetic field that it creates? Well, the equation to determine the magnitude and direction of the magnetic field is given by mu naught over 4 pi. All right, so mu naught is the permeability of free space. Its value is 4 pi. I know it's another 4 pi times 10 to the minus 7, okay? Tesla meter over amps, I believe. So it's basically kind of like magnetism's constant, okay? Like we had epsilon naught for electric fields, we have mu naught for magnetic fields, all right? It's permeability of free space. That constant times charge in velocity vector crossed with r hat. All right, so what the heck is r hat? You may remember r hat from our discussion on electric fields. It has the exact same definition. R hat is the vector that points from the charge to the field. Okay, the charge that's creating the field to the place that we want to know the field. So, question is, what if we want to know what is the magnetic field directly above positive Q? What would be our r hat in this case? The r hat would be pointing straight up along the y direction. Okay, why? Because it's the direction from the source to the field, right? The source of the field to the place that we want to know the field. So r hat is a unit vector pointing from the source to the field point. Okay? The v vector would obviously be in the x hat direction. And then we are dividing it by r squared. So what is r squared? R has the same definition as what we did in electric fields. R is going to be the distance between the source and the field point. So this would be r right here. Okay? Simply that distance between the charge and the place that we want to know the B field. So if we kind of put all that together, what do we see? Well, our magnetic field magnitude is going to be mu naught over 4 pi QV over r squared, right? Because this is 1. The magnitude of a unit vector is 1, so there's no r here, right? That's the number 1. And then the direction of B is going to be, well, if I change this to, let's change this to vector notation. The direction of B is going to be the direction of V cross R, which is X hat, or let's just do I hat cross J hat, which is what? It's K hat, right? I cross J is K. So our magnetic field is going to be mu naught over 4 pi QV over R squared K hat, all right? So it's kind of a little bit of a complicated equation, namely because R hat is kind of difficult to imagine, right? It's a little bit of an abstract definition, but just always refer to like the blue text that defines what this variable is. Okay, don't just start making things up. Read what it says. It says it's a unit vector that points from the charge to where we're measuring the field. So, all right. And then there's a cross product in there, so that can also complicate things. So the direction, like I mentioned before, it's given by a right-hand rule, okay? And the right-hand rule, you can use both versions of the right-hand rule. So we've talked so far about two types of right-hand rules, right? The first one is you put the fingers in the direction of V, and you curl them, and then you curl them into B. And wherever your thumb ends up is F, right? But we don't have an F here. So what we're doing is we're curling V into R hat, okay? So to apply the right-hand rule to this equation, we're curling V into R hat. And then the direction of our thumb will be B. Okay? So that can be a little difficult. Why? Because, you know, your R hat is going to change depending on where you want to know the B field, right? If you want to know the B field over here, well, your R hat is going to be something like I hat. If you want to know the B field over here, your R hat's going to be J hat. This would be negative I hat, okay? So a nice way to kind of give all the directions at once is to do the second right-hand rule. The second right-hand rule, I'll just kind of like write it down over here. The second right-hand rule, well, I mean, I don't need to, it's right here. Right? You put your thumb, here's the second right-hand rule. You put your thumb in the direction of the moving charge, okay? So in this picture right here, the charge is moving into the page, right? It's moving farther away from you into the page. So it's moving, you know, down that way, okay? Down into your table or into your screen. So you would put your thumb in that direction, and then you would curl your fingers the way they would naturally go when your thumb is pointing into that page. I don't know if I can draw this, but we're going to try, right? There's my creepy, weird fingers. And my thumb is, you can't see it because it's into the page, okay? And then you curl your fingers around in a circle. All right, you curl them around in a circle. And if you want to know the direction of the B field up here, you pause your fingers there, okay? You pause your fingers there, and when you do that, you'll see that your fingers are pointing this way, right? And your thumb is into the board. And if you pause your fingers here, you'll see your fingers will be pointing this way. And then they'll be pointing this way and this way as you curl them around the circle. So doing it the second way, you know, gives you basically, it shows you all of the points and the handedness of the B field. If you want to know the B field in one location, you could just use number one. They both work here though. Okay. So we talked about the magnitude and direction of a magnetic field created by a single moving charge. Let's do an example where we put this into action. So we have two moving charges here, all right? The one on the top is a proton. It's moving to the left. You can see that right here, right? It's moving along the negative x direction. And then we have another proton's moving to the right along the positive x direction. What we want to do is, and they're moving at the same speed. At this moment in this picture, we want to find the electric and magnetic forces on the upper proton. All right? That's why you see the force vectors are drawn on the upper proton. We want to find the forces on that upper proton. Due to what? What the forces due to what? The bottom proton, his existence, right, means he's producing an electric field that points away, directly away at all points in space. So right up here at the location of top proton, there should be an E field right there pointing up. Okay. Well, bottom proton is not just sitting there, he's actually moving to the right. So not only is he going to produce an E field, but he's going to produce a B field. Right? He's going to produce a magnetic field. And the direction of that magnetic field is actually this way. But we're gonna talk about it. Why is it this way? All right, we're going to use the equation that we just looked at here that doesn't really have a name. All right, we'll use that equation to figure out that. So let's do this example. Oops, there's the homework. Here we go, 28.1. Okay. So we want to find the force due to the magnetic field and the force due to the electric field. Well, in order to find the force, we need to find the actual field values, right? So that we can figure out what the force is. So let's do that first. Let's take it way back. Let's find the E field. Let's find the E field at the location of the upper proton. Okay? This is the E field created by the lower proton. We can just go ahead and just straight up write what that is. It's 1 over 4 pi epsilon naught Q over R squared, right? Q being the charge of the lower guy, because he's the one creating the electric field. R being the distance between the source of that field and the place that we want to know the field. So we'll just call that R. Okay? That distance right there. So what's the direction of the E field? Directly away from the guy creating it, right? So if we want to know the field right here, directly above that charge, pretend like there's no charge there. Actually, let's go ahead and just redraw this picture. Let's redraw this picture with only the lower proton. Okay, and we just want to know the field right here. Okay, which happens to be the location of the upper proton, but we're just going to pretend like it's not there for now. So the E field then would point directly away from lower proton along the y-axis, right, which is j hat. So E then would be 1 over 4 pi epsilon naught Q over R squared j hat. So let's find B now. Okay, so we're finding the B created by the fact that that lower proton is moving along the x-axis to the right at speed v. So we're going to use the equation that we just learned. All right, it's going to be Q v cross R hat over R squared. So let's fill in these blanks. What's the V vector? Well, it's simply the velocity in the I hat direction. We're going to cross that with the R hat vector. What's R hat? R hat is the vector that points from the source, which is the bottom proton, to the place we want to know the field, which is up here at that black dot. So our R hat is going to be in the y direction, right? And this is a unit vector, so there's nothing next to it. It's simply R hat is j hat. It's not R j hat. It's not one, well, it's technically 1 j hat. What is R squared? Well, if we just call this distance R squared is just R squared. And so if we move all of our constants to the left, right, all we need to do is perform I cross J And what we get is K, right? I cross J is K. So the direction of the magnetic field is in the K hat direction or the Z direction. So it's actually like this, right? Parallel to this axis. Just like in the picture now, right? Now it makes sense why B is there. Why B is looking that way. So there's B. B is in the K hat because V is in the I and R hat is in the J. And I cross J is K. So we're not done. What are we asked? We're asked for the force. The force of the electric field and the force of the magnetic field. Well, force of the electric field, we can do that all day, right? Where Q is the charge of which one? The top proton, right? He's the one feeling the force, right? He's up here at the location that we know the electric field value. So if we put him there, he will feel the force of that electric field. So that's the charge of the top proton. And then this E is simply that, right? Which this Q is from the bottom proton. So we'll just spell it all out. We get 1 over 4 pi epsilon naught. Q1, Q2, they're both the Q. They're both protons, so it ends up being Q squared over R squared. And that is in the J hat. Right? Because all we did was multiply the E vector by a scalar, so its direction didn't change. Now, if that Q was negative, well, then we would have a negative J hat, right? But it's not. They're both positive. So what about the force, the magnetic force? Well, we're going to have to go back to chapter 27, right? Remember, magnetic force is not like the electric force where you just multiply it by a scalar. You actually have to do a cross product to find the magnetic force. And so what are the elements of this cross product? Well, this is going to be the charge of the top proton, right? Because he's the one feeling the force. This is the velocity of the top proton. And then this is the magnetic field that he's moving in. That's the field created by bottom proton. All right, he's the field created by bottom proton, which we found right here. Beep, beep, beep. Right, that guy. So let's spell all that out. Q, V in the negative X, I'll do it, negative I hat direction, right? Let's take a look at the picture again. What direction is top proton moving? He's moving in the negative X direction, right? So this is the velocity of the top proton. He's moving in the negative X direction. We're crossing that with this stuff right here. Mu naught over 4 pi Q V R squared in the K hat. I'll just put little parentheses around it so we can just see the directions better. So when we do this cross product, we're going to bring all these constants out to the front. So we get mu naught over 4 pi. A Q here gives me a Q squared. A V here gives me a V squared all over R squared. And the direction of that is negative I hat cross K hat. So what is negative I hat cross K hat? The way that I would approach doing that is I would first pull out my negative and look at I cross K. So I cross K moves in the counterclockwise direction. So that's going to give me a negative J hat. So I have my negative out here. This becomes negative J hat. And then my negative times my negative is simply J hat, right? So my force on the top proton is going to be mu naught 4 pi Q squared V squared R squared J hat. Okay, so we're pretty much done. Boop, 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 boop. These are our answers, right? These are the forces that the top proton feels due to the electric field and the magnetic field created by the bottom proton. That's what we answered. There's another part to it where it asks us to compare the magnitudes. We can do that real quick. It just kind of illustrates a cute little relationship. It's cute. It's fun. All right, we're going to compare those magnitudes by taking the by taking their ratio. So if I do FB divided by FE, mu naught over 4 pi Q squared V squared over R squared, right? These are magnitudes. I'm going to multiply it. Instead of dividing by FE, I'm just going to multiply by its reciprocal, right? That's totally legal. So the stuff in the denominator of my FE is going to go in the numerator. And then the stuff in the numerator will go in the denominator, right? And then we can see stuff cancel right away. The Q's go away. The R's go away. The 4 pi's go away. What we're left with is mu naught epsilon naught V squared. Okay, so what's so great about this? Well, what you will come to learn in a couple of chapters, but I'll tell you early, is that the speed of light can actually be defined in terms of these two constants, mu naught and epsilon naught. And it turns out that the speed of light, which you know is 2.998 times 10 to the 8 meters per second, right? And there's a bunch of decimals that go after that. The way to write it the most precisely is like this. This will give you, this irrational number will basically give you every decimal you need. This is the speed of light, okay? So I'm going to rearrange it a little bit. I'm going to square both sides and then take the inverse. And so what I see is that 1 over c squared is actually equal to mu naught epsilon naught. Okay, plug that in here. And what I get is F, the ratio of the magnetic force to the electric force is actually the ratio of the speeds to the speed of light. And so what this tells you is that the force, the magnetic force, will always be a heck of a lot smaller than the electric force. All right, why? Because this V can never exceed c, right? The speed of anything that we know in the whole wide world, in the whole universe, nothing is faster than the speed of light. So the velocity of any particle, charged particle moving will never exceed the speed of light. And so this ratio will always be a number less than 1, okay? And that's basically the cute thing that it shows you, right? And if you look up here in this picture, you can see that, look at the magnitude of the force vectors, right? They drew them to some scale. FB is always going to be much smaller than FE, and that's basically what this example is telling you. Let's extend that equation that has no name. This one right here, the magnetic field due to a point charge with constant velocity. And we're going to extend that to a small piece of wire segment carrying a current, okay? In the same way that we extended the force QV cross B, we're going to turn that, we turn that into IL across B. Well, now we're going to turn the magnetic field due to a single charge okay, we're going to turn that into a more generalized version that is the magnetic field due to an infinitesimally small current element, all right, basically replacing QV with IDL. And that becomes the Biot-Savart law, okay, which has a name. And basically the operation is identical, right? except now we're just considering a different case, the case of a current flowing through a conductor, not just a single charge flying through space, okay? So definitions are all the same, right? Except now we have these little differentials here, like we did when we were determining what DE was, right? And these little differentials are basically telling us that in order to find the total field due to the entire segment, we will need to do an integral. So I'm not going to make you guys do an integral. All right. So don't worry too bad about that. We're going to kind of skip the integral stuff just for the sake of time. Let's do this example where we are going to employ the Biot-Savart law. All right. And in this example, we're going to find the magnetic field created by this little piece of wire segment right here. And we're going to find the magnetic field at two places. At a location P1, directly above the wire segment, and then at a location P2, which is at an angle 30 degrees from the wire segment, okay? So in this example, we're going to be finding the magnetic field at P1 and P2. All right, so let's write down our knowns here. We're going to find the magnetic field at P1 and P2 due to this 1 centimeter piece of wire that has 125 amps of current flowing through it. So we know that the current is 125 amps. And there's a coordinate system on here. And from that coordinate system, we can see that our DL vector is going to be DL in the negative x hat direction or negative I hat direction. And what is that DL? It's 1 centimeter, okay? 0.01 meters in the negative I hat direction. And, so we're using the law of Biot-Savart, which states that the magnetic field, small piece of magnetic field, due to the small piece of current segment is mu naught over 4 pi I dl vector crossed with r hat over r squared. So we need to figure out what's r hat. Well, we're going to have a different r hat for P1 and P2, right? Because r hat is defined as the direction from source to field point. Okay, so for P1, our r hat will be in the y direction or j hat direction, right? And then for P2, you'll see that r hat has an x and a y component. Okay, so we'll talk about that. Let's tackle P1 first. So question is, what's the magnetic field that small piece of wire segment at P1? Well, it's mu naught over 4 pi I dl. What direction is dl? dl is in the negative I hat. That's going to be crossed with r hat, which happens to be j. And we were given r. I won't write it down yet. Right, we were given r. This is r, 1.2. So let's write down that one given over here. Okay. So let's go ahead and perform this cross product and then plug in all of our knowns. So we're crossing negative I with j. So when you cross I and j, you're going clockwise. All right, which means you're going to get a positive k. So I cross j is positive k. But what we really have is negative I cross j, right? Because there's a negative sign there. So our result is going to actually be negative k. And Oh, looks like I have it written here from previous, right? So let's plug everything in. I already have it written down here nicely. So our mu naught over 4 pi, our I is 125, our DL is 0.01. The result of negative I cross J is K. Here's the negative. And then it's divided all by 1.2 squared, right? Where R is 1.2. That was given to us. R is the distance from the source to the field point. And so when we plug all that in the calculator, we get negative 8.7 times 10 to the minus 8 Tesla in the k hat direction. In other words, well, what we really have is 8.7 times 10 to the minus 8 Tesla in the negative k hat direction, right? You can read that two ways. So that is the magnetic field due to that 1 centimeter piece of wire at location P1. So what about location P2? Let me go ahead and erase all this. And we'll start it over. So at location P2, the only thing that's changing is our hat, right? Everything else is the same. Take a look at the figure. The distance that P2 is from DL is also 1.2. So our R isn't changing, right? The only thing that's changing is our hat. We're now in a slightly different location relative to DL. We are 30 degrees from the current carrying wire. And so our hat is actually going to have two components. Let's go ahead and draw that little bit of, so this is X, this is Y, here's positive X, okay, here's P2, and that's 30 degrees. So our hat is going to be along that line right there. So it's definitely going to have an X component and a Y component, right? Let's draw that right triangle to figure out what those components are. Our hypotenuse of the right triangle is the R hat vector, which has a length of 1, right? All unit vectors, all hats, mean the length of that vector is 1. This angle is 30. It's given to us. So that would make this the R hat component in the X and this the R hat component in the Y. Okay, and notice that this R hat is pointing to the left. So the X component is going to be negative, right? And this one is pointing up, so it's going to be positive. So let's figure out what Rx and Ry are. We don't need to set up similar triangles because we are given the angle. Okay, so we know we have everything we need to figure out what the components are. So Rx is going to be simply R hat, which is 1 times cosine of 30 degrees. Why? Because it's the adjacent. Ry, I'll just say R hat Y, is going to be magnitude 1, right? The hypotenuse of that triangle times sine of 30 degrees. And so then my R hat vector is going to be negative cosine 30 I hat plus sine 30 J hat. I'm sorry if you hear my dogs wrestling in the background. Let me shoo them away real quick. All right, so dogs have been shooed away. R hat has a negative X component, positive Y component, okay? And it's time to plug all that in and perform the cross product. So let's do that. So we're going to have our mu naught over 4 pi IDL in the negative I hat with our R squared. We're going to cross that with negative cosine 30 I plus sine 30 J. Okay, let's distribute. Or, let's distribute was the right word. So when we distribute that, we're going to have two terms. we're going to be crossing mu naught 4 pi I dl r squared. We're going to be crossing negative I hat with I hat. Okay, or technically it's negative I hat with negative I hat. Either way, it gives us a 0, right? Plus 2 terms, right? This constant gets distributed as well. Now we're crossing negative I hat with sine 30 j hat. And this term is 0, right? Because it's I cross I. So our dB eventually is going to be that number. I'll just leave that there. Our dB is going to be mu naught over 4 pi I dl over r squared negative I hat. Well, let's move this sign over because I know I'm going to get I'm going to get non-zero, right? So let's move this sine 30 over. And what I'm crossing now is, to get my direction of this B field, is negative I hat with J hat. So I'm crossing I and J, right? I'm going clockwise, so I'm going to get a positive K. But I have that negative sign there. Right, so, oops, that's a J. This is a K, right? So my result is negative K. So I can throw my negative in the front or in the back, doesn't matter where you want to put it. Sine 30, K hat. All right, let's plug in all those numbers. Negative mu naught over 4 pi. 125 amps, 1 centimeter dl. Our R was still 1.2 meters squared times sine of 30 degrees in the K hat. Plug all that in and you get negative 4.3 times 10 to the minus 8 Tesla in the K hat. All right, so all we did was plug in some values. We did the cross product, on 2 terms. So we had to distribute that. We had to do I cross I plus I cross J. All right. And so that can be a little tricky algebraically to write out. I wrote it here as 2 terms. Okay. One of the terms went to 0. This is what I was left with. And that is the value of the magnetic field due to the small piece of current carrying wire, okay, at a distance 1.2 meters away. So that's a small field, right? 10 to the minus 8 Tesla, that's really small. 125 amps, that's a lot of amps. So just being 1.2 meters away from a wire carrying 125 amps of current, you really don't feel much of a magnetic field due to that. Okay, and that's kind of real life values here. Okay. So we just finished this example, and the idea here is that we extended this no-name equation into the Biot-Savart law, which you see has differentials in the equation, right? Which clue you into the idea that in order to find the entire magnetic field due to the entire length of the conductor, you must, eventually integrate both sides, okay? So I'm going to spare you these integrals, and I'm going to just instead walk you through a brief derivation of one of them and come up with a relation that, we will need to use later on in the chapters. And so you're going to find this eerily familiar to when we found the total electric field due to a segment of charge, right? A linear segment of charge. Well, now, instead of a linear segment of charge, we have a linear piece of wire with current I flowing through it, okay? And so the first thing we're going to do is we're going to find the infinitesimally small piece of current, the infinitesimally small bit of magnetic field due to that infinitesimally small piece of current, okay, or current carrying wire, DL. And so we set that up in this form, right? So basically we come up with dB right there, and we're going to integrate from negative A to A. So we're going to have a fun little integral there, table integral, and its result is going to be this right here in the purple box, right? This is going to be the magnetic field due to the entire piece of wire. All right, from negative A to A. So this whole wire of length 2A, the magnetic field due to that piece of current carrying wire of length 2A is going to be this value. And so what we're going to do in the same way that in that example where we found the electric field due to that line charge is we're going to expand this and take a look at this function when we let x become much, much larger than a. So what does that mean if we let x become much, much larger than a? That means that we are very far away from the wire, and we're so far away that the wire looks like it's infinitely long, okay? So in other words, instead of x much, much larger than a, what we could say as well is that we are letting a approach infinity, all right? And so when you perform the limit on this function here, what you find is that you end up getting b equals mu naught over I divided by 2 pi x, okay? Where x is that distance from the wire. Well, instead of using the letter x, we're instead going to use the letter r, where r is the distance away from the wire, okay? So from this kind of complicated looking equation, we get a much simpler one. If we assume that we're sufficiently far away from the wire so that it looks like it's infinitely long, we can reduce the magnetic field magnitude to this simple equation right here. Okay, mu naught I over 2 pi r. And so let's take a look at the, right, so that gives us the magnitude of the field. So let's take a look again at the direction. And we talked about this in a previous slide. So we use the right-hand rule, the thumb version, to determine the direction of B. So you put your thumb in the direction of I, and then you curl your fingers around I, all right? And so that when you're on top of I, your fingers are going to be pointing out of the page. When you curl them around to be below the current I, the B field will be pointing into the page. And so we can look at it in two different perspectives in addition to this, right? If we look at the wire head on, so it's either coming at you or going away from you. Let's look at the case of it coming at you first. I'm trying to delete this because I had recorded all of this and I don't know where it went. It just completely disappeared off my iPad. So here we are again. So we have the current coming out at you. All right, so your thumb is going to be pointing out of the screen. And then your fingers of your right hand are going to curl in the counterclockwise direction, right? So in that perspective, your B field on top of the wire will be to the left. Your B field below the wire will be to the right, and the direction of the B field to the right of the wire will be up, to the left of the wire will be down, right? Okay. What about if the current is flowing away from you? Well, the B field is still going to make circles around the current, except now your thumb's going to go into the page, and the fingers of your right hand will go clockwise. And all those directions are going to flip. So when you're to the right of the wire, B will be going down. When you're to the left of the wire, oops, did I draw? That should be an up arrow. Sorry about that. When you're to the left of the wire, B will be pointing up. When you're above the wire, B will be pointing to the right. And when you're below the wire, B will be pointing to the left. Okay? So perspective matters, all right? Use your right hand, thumb in the direction of the current, curl those fingers around. That'll tell you either the clockwise or the counterclockwise direction of B. And then taking the tangent of those circles at different locations will tell you the direction of B. And so, for example, if you were kind of, not off axis, but if you're not in the north, south, east, west position, your B will be at a slight angle, right? Won't be directly up, down, left, or right. All right, so let's do this example where we have a long straight conductor carrying 1 amp of current, and we're asked what is the distance from this current, from the axis of this conductor, right? So basically, how far are you from the wire to feel a magnetic field that is 0.5 times 10 to the minus 4 Tesla, which is roughly about the Earth's magnetic field in Pittsburgh, Pennsylvania, okay? Which is not too much different than the magnetic field that we feel here in Florida. Okay, it's pretty close. So let's go ahead and figure that out. So we're going to use the fact that the magnitude of the magnetic field, a distance r away from a long, long wire, is mu naught I over 2 pi r, okay? And we know that that magnetic field is 0.5 times 10 to the minus 4 Tesla. And we know mu naught, we know 2 pi. We're told that I was 1 amp, and we're asked to find this distance, right? The distance r from the axis of the conductor. So really easily we can solve for r here, right? R is going to be equal to mu naught over 2 pi, 1 amp over 0.5 times 10 to the minus 4 Tesla, right? Just solving for r. And if I plug all that in the calculator, so recall that mu naught is 4 pi times 10 to the minus 7, okay? And so this kind of cancels to 2, right? So that'll just make, a little bit of less typing in the calculator. So we'll have 2 times 10 to the minus 7 multiplied by 1 divided by 0.5 times 10 to the minus 4. And what do we get? We get 0.004 meters, which is roughly 4 millimeters, okay? So what this is telling us is that if you happen to be charging your phone and you are using the little square Apple charger, not the big one, but the little square brick, okay? If you read on that brick, it says that the output is 1 amp. Okay, so if you're charging your phone and you are 0.004 meters away, or if you're 4 millimeters away from that wire, so basically you're sticking that wire like on your eye, all right? The magnetic field that you feel from that wire will be roughly equal to the Earth's magnetic field. All right, so in other words, not a huge amount. All right, you're not feeling a lot of magnetic field generated by wires carrying current to charge your devices. Biological magnetic fields, the magnetic fields that exist in your body due to moving charges in your body are very, very small as well. So, You're not going to be influencing really any of your biological structure by charging your phone, or, even if you're close to something that has maybe 100 amps running through it, right? If we change this one to 100 amps, so multiplying it by 100, we are basically still feeling, not a huge magnetic field at all. All right. So all of these devices in your home, now that said, everyone's body's slightly different, right? But in general, you do not really feel much of a magnetic field due to all of the currents flowing around in your home. All right. So that's a really interesting example that kind of, ties back to some kind of real life examples of, how we interact with magnetic fields on a daily basis. So what I'm going to do is I'm going to break now and create a new video. We're going to start off at example 28.4, where instead of one wire, we're going to have two wires that are simultaneously creating fields and feeling fields. Okay, so there's going to be some bookkeeping here, so your mind should be fresh when we get to this example. Okay, so I'm going to end this video here, and we will pick back up on 28.4.